So for the code, I try to show you the very simple calculation using the Q, K, and V. Do you still remember this one? Okay, we have query, key, and value. This is for the attention. And we can make the scratch. Okay, so I call this is the scratch for the attention. We use the scale dot product attention. If you still remember, when we do this, so the scale dot product attention is the basic of the transformer, and we use the key Q and V, and we are creating the attention by using the softmax function. So we multiply the Q and K, and then we divide with the decay, square root of decay, and multiply with the V. I think the very easy way to do the code is like this one. We have the Q, K, and V, and then we are going to do the dot products. Dot product means the matrix multiplication. So we have Q and K dot T means this is the K transpose. And then we can do the scaling. Scaling here, scale by the square root of that. Square root of that means we are looking at the Q, and the depth is based on the shape. This one, -1 is the last one. And we can make the scale attention logics. So the this is the matrix multiplication Q and K divided by the square root of the gap. And we can apply mass if provided. So usually we use the mass by multiplying with a small value. And after that, we will apply the softmax. So the softmax function we learned from the previous one. The softmax function is using the we learned from the first part. Okay, we can use this softmax function, and the formula will be like this one. So we just use the exponent from the E, and we will get the attention weight. And at the end, so we are looking at the output. The output will be the matrix multiplication from the attention width and V. So let's look at an example. I have one example of the sentence, Alice is good. For the first, before we do the attention, we are going to make an array, or this we call it as the embedding. So the embedding, you can use any of the algorithm. For example, you can use word to fact, you can use glove, you can use fast text, and etc. Okay. So we learn those things at the first part of our lecture before mid-exam. Or in this case, I generate randomly. So if you still remember, whenever we make a text, it is a kind of representation. What is this representation? Let's say, I have Alice, and then is good. So I can also have this is Alice is good. And this representation means I know this is Alice, and yeah, the representation for the Alice will be very high because it is representing its own word. And then after Alice, yeah, there will be some embedding score. How big is the possibility after Alice is? So let's say, yeah, the score is 0.5. And after Alice, we can see if it is good, then the score is 0.1. So the embedding score can be represented with some random values or using the representation like glove and word to fact and etc. This is also for the word is. The word is we have 0.4, 1, 0.5. The good is 0.2, 0.2, and 1. And using this embedding, we can do the attention weight calculation. So let's suppose the Q, so the Q is the array of embedding Alice, and then embedding is, and embedding good. So usually when you do the things in the attention, you will have this embedding, and this embedding can be represented in any of values. Now let's assume that the K equals to Q, and let's assume the V equals to Q. So usually it can be represented with another value. And we can just use the scale dot product attention that we have previously. We just multiply the Q, K, and V. So if you run this, so if you run this code, then you will get the attention weights. It means the similarity between words. And yeah, we can get the output, which is the weighted representation. So what does it mean by this one? It means that after we do the Q and K and V multiplication, we know that the word Alice have the representation as much as 0.4 to the word Alice itself. It has a representation 0.3 for the word is, and it has 0.248 for the word good. The next row represent the word is. So we can see 0.3, 0.4, and 0.28. And this one, the last one is for the word good. So if we have the word good and the representation with the word Alice is 0.26, and the representation for the word good is 0.33, and the representation good and good is 0.39. Okay, so this is based on the calculation. And then the output or the weighted representation, we can also interpret the same like this one, but the value is different. So we can use this one for the weighted representation for maybe encoding, or maybe for the decoding, or you can put this weight into other neural network and etc. Okay. So this is the attention weight that can be fitted into RNN, LSTM, or other kind of neural net. So in the transformer block, actually, yeah, it is a collection of the Q, K, V, and let's say that we may have the multi-head attention. So what is the multi-head? We learned from the slide that we want to focus on several words. So if you still remember, when we learn this one, there is a word, Bob is very cute and he is a dog. And we want to focus on several words. Let's say, I want to know that the word he, there is a relevancy with the word dog, there is relevancy with the word Bob. So it means I want to make an attention. So the attention, there will be multiple attention, not only one attention. Then we can make the multi-head attention for that purpose. So this is the multi-head attention from the scratch. Okay. If you know, this is the constructor. So let's make the random value for the head. How many heads do we need? And yeah, here is the number of heads. It is defined, and this is the embedding dimension. And then this is the depth. The depth means the dimension divided by the head. So we can create a random number to generate a Q. We can create a random number to generate a K, and we can generate a random number to generate the V. And then we can make just a simple feed forward layer weights using random value. And again, we will do the scale dot product. So the scale dot product means the multiplication of Q, K, and V. And now we do not use one attention, but we have multi-head attention. If it is multi-head attention, then we just have one more repetition, or we call this is the for loop. So the for loop means I will focus on the first head, and then the next head, and then the next head until the number of heads. So this is the same with the scale dot product. At the end, we can just concatenate. Concatenate means we just combine. We combine for every of the head output. And the combination, we just do the dot. Dot means just the product of multiplication. For the feed forward, it is a simple feed forward with ReLU activation. So if you want to know more about the ReLU activation, this is a simple ReLU application by finding the maximum of the XFF, or this is the dot, from the value multiplied by the weight in that network. And then we do the forward by first checking the self attention layer, and then we do the attention output, and at the end we have the feed forward layer. So this is the function for the multi-head attention. And yeah, we can do something more with what Alice is good. Previously, we have the embedding with 3 multiplied by 3. So 3 multiplied by 3 means I know the word Alice and I want to know the score with the word Alice itself. I want to know the word is, and I want to know what is the score with the word is and the word good, and I want to know the word good. So if I can represent the score, then I know the importance or the weight. If the word Alice, how big is it is important with the word Alice itself, and so on. Now, you can see there are 6 embedding, not only 3. Why? The words are only 3, but why the embedding there are 6? I will explain later. Commonly, we can just easily look at 3 multiplied by 3 with the 3 words. But we can do something for. So the idea is the same. You can using the stacking. We have the X is the stack from the embedding Alice, embedding is, and embedding good. And then we create the transform block. In the transform block, we have the embedding is 6, and then let's assume the head there are 2. So we can just forward the transform block. So after we create this transform block, we create the forward, and then we can see the output. So you can see the output is this one. This is a number. So what does the number represent to? So I give this explanation. So why do we have 6 dimensions of embedding? Well, there are only 3 words. So the 6 values capture various features and aspects of the words. For example, we can represent the semantic or the syntactic rule of the sentence. For example, let's say Alice show that the weight is 1, 0.5, 0.2, 0.3, 0.7, 0.1. So 1.0 means how the score of Alice represent to the word Alice itself. The second one, maybe the word Alice represent the score to the word is. The third one, the word Alice represent to the word good. The last 3, there might be some additional features. For example, Alice represent gender-related features. So we have a score 0.3. Okay, maybe if it is related to female, then the score is 0.3. If it is related to male, maybe this is 0.7, and so on. The second value, the second additional value, can be represented, for example, if it is a noun, or if it is a pronoun, or if it is an adjective, and etc. So we can have another score. The other score can be representing the syntactic behavior. For example, whether it is a subject of the sentence, or it is a verb of the sentence, or it is an object of the sentence, and etc. So every score can have a representation. That's why we call this kind of embedding is a text representation. I show you very simple array like this one, but as a matter of fact, when you use the real word embedding, for example, you use the word to fact or bird, the dimensionality is often much larger. So the embedding not only 6, not only 10, but it can achieve like 300, 700, and so on. And this will encode more nuanced information. So you can see, if you still remember the text representation, we have POS, part of speech. So we have the POS tagging. It means I can see that maybe one word represent subject, another word represent verb, or sometimes we have the basic verb or verb in the form of past and so on. So we can use the POS tagging, or we can have the name entity recognition, whether it is a name or whether it is an organization, and etc. So everything can be represented in the word embedding. For using the transformer, yeah, that's the very basic one. I created the code from the scratch, but maybe you have no interest to make the code from the scratch. So let's just use it. How we can use the transformer into the application. So for the transformer, actually there are several libraries that we can use. For example, we can use PyTorch or you can use TensorFlow, or you can use other library. Let's use the Torch, and let's use one transformer from BERT. So we will learn about BERT model and what is BERT in the next class on Thursday. So BERT is one of a pre-trained model. The pre-trained model means the model that has been trained with very big data, and we can just reuse it for our text analytics purpose. For example, in this case, I would like to use the BERT tokenizer, and in the BERT tokenizer, there are several pre-trained. For example, this is using the BERT base uncase. So this is free. You can use for your text analytic purpose. And the model that I want to use is from the pre-trained BERT base uncase, and I would like to use attention. So we already learned about the attention previously. So output attention true means I will use the attention from this BERT. Now I would like to see a text. Okay, let's say Alice is a good friend. And you know, when we do the text analytics, we need to tokenize. Tokenize the word. So the tokenization will use the tokenizer from the word, and then we will make it as a tensor. You know what is tensor? If you know about matrix, so matrix is just 2 dimension. Tensor, usually we represent the numbers more than 2 dimension. So we can represent in 3 dimension, we can represent in 4 dimension, and so on. So they use the tensor to represent the text. And then I will show you a simple tensor with the word text like this one. After we have the tensor, we will make the input ID according to the inputs. And then we are making the output based on the input using the model. And then we are going to look at the attention. So the attention means the weight that we created, like what we saw before. We can use the matrix multiplication. But in this case, the matrix multiplication has been provided from BERT. So we have the attention weight, and after we have the weight, we can see the attention shape. So let's inspect only the first layer and the first head. The first layer means the layer 0, and the first head means the head 0, and we are looking at the attention weight. because if you look at all the widths, it will be very long. So you can see only the width in the first layer and the first head. And let's make it as a number. And so you can see here, this is the attention width in the layer 1 and in the head 1. So everything will be a number, and as you know, this is a black box. It is not easy to interpret this one once you put it into the neural network. You can see this network. And you can see this network by something like this one. So the tokenizer can be converted into the input ID. So the input ID means we want to check each of the numbers into the tokens. The tokens mean the word. So this is the plotting mechanism. So I would like to plot the attention width, and the attention width, it will be based on the key and the query. And I would like to see the attention width with the layer 1 and the head 1. So you can see here is the width with the heat map. So the word Alice, and the word Alice. So the color is rather in the blue. Maybe the width is not that strong. If it is strong, then it shows the yellow color. So this is the representation width is high. And purple color here, the representation width is blue. So we can also look at the bird vis. It means this is for the bird visualization. Okay, so I run again from the bird, and you can see this layer by layer. So layer 0 means you can see everything, and layer 1, so you can see that the CLS. What is CLS? CLS represent the class. So CLS represent class. And for every of this word can have a relation with the class itself. So the class usually is only a target that we want to look at. If you change the word Alice, then you can see that, okay, the word Alice is representing with the class. The word is also representing with the class, and it's also has a connection with the sep. Sep is the separator. It means we finish this sentence and there will be a separator with the next sentence. How do we know that it is a separator? Usually we look at the ending of sentence. For example, in this case, we have dot. The dot, when we write something, Alice is a great friend. Dot. So it means it is the end of the sentence. Then we will go to the next sentence. That's why we have a separator. And then we will check the relationship for every of this one. You can see that the word has all relationship to the CLS, or it is related with the class. And you can look at the second layer, and you can see on the third layer, and you can see on the fifth layer, and so on. So it is to see how the attention work for every of the word. Of course, it's not obvious. We cannot see clearly here because the word is very short. So using this kind of attention, we can have a text generation. For example, okay, let me use another pre-trained model. Let me use the GPT-2. The GPT-2 is still free for you to use if you want to use a pre-trained model like the bird of GPT-2. So the idea is the same with the bird. We can just call the model and then we reuse it to create the model. And let's say I have the word Alice is a great friend. Now I'm going to use a tokenizer and we are going to make the encoding. The encoding, we use the tensor with the PT. PT is the PyTorch. And then let's generate a sentence. Let's assume the maximum length is 12 and the written sequence is 1. So it means I will have only 1. And you can generate the text. The generated text will be from the decoder. And let's just make into one sentence. If you run this one, you can see this one. The word Alice is a great friend. So the generated text is, she is a great person. So we can make a longer sentence, or the GPT-2 can create more words after we have one sentence. So the remaining is only explanation how you will do with the tokenize using the tensor. For example, let me go back to the bird. We have the Alice is a great friend, and I want to see what is the meaning by the token. So the token here, you have like this one. Usually we have this as 101 represent the CLS. It is representing the class that I show you from the first part. And then 102 is representing the SEP or the separator. Every of this one representing the ID of the word that we want to look at. So the 5650 is the ID for Alice. 2003 is the ID for the word is. This is an ID for the word a. This is ID for the word great. And this is ID for the word friend. And this is ID for the word dog. So we have every ID and then we want to put all of them into the token and the attention mass. If it is available for the token types, then we put 1. But if it is not available, we can put 0. For the attention mass, yeah, we can put 1 if it is available. So as I mentioned before, PT means PyTorch tensor. You can use TF for the TensorFlow, or you can use NP if you use NumPy, or you can use JAX as the Java X tensors. So this is the explanation about the input ID, token type ID, and the attention mass. For the token ID, it is representing for every of the word that we have. That's why if your word is very long, then the ID will be so many. And the token type ID, if 0 means the token belongs to the first segment, and if it is 1, the tokens belong to the second segment, if present. It means if you have many words, then there will be different segments. And the attention must mean the token to be attended to, or the real token, or the tokens to be ignored, means the padding tokens, or some things that we do not need to consider for the attention. So the last one that I want to share is how we can use the pre-trained model as like question and answer. Yeah. So I use again the GPT-2 instead of BERT. And then let's make the text, what is the best way to prevent illness? So I put a question and I would like to ask to the GPT what will be the best text generation or what will be the best answer based on the model. So I can do again the encoding. So the encoding means change the word into encode and we generate the word by decoding. And by using this mechanism, we can get the answer. What is the best way to prevent illness? The best way to prevent illness is to avoid smoking. So this is based on the GPT-2. Okay, that's all from this class. Any questions, comments?